All right, welcome to day 15 of the Calc Notes. Now today is a little trickier. We're going to talk about the max-min theorem and their intermediate value theorem. And they're actually things that make a lot of sense, but I think it helps just to hear them talked out a little bit. First, some warm-up questions, because there is a quiz on limits coming up, and this is some of the quiz questions or types of quiz questions you could see. So the first one's a pretty straightforward limit. Evaluate limit as x goes to 0, 3 minus radical 9 minus x all over x. Okay, so remember you always want to plug in first to see if it's anything other than 0 over 0. So that's what I have written over here. When I plug in 0, 3 minus 3 is 0, 0 is obviously 0, so it is. Anytime you see a radical, you want to think multiply by the conjugate. So 3 plus radical 9 minus x, top and bottom. Remember you want to multiply out the conjugate, so it's going to be 3, middle terms cancel, minus, keep that 9 minus x in parentheses so we can distribute the negative. On the bottom, don't multiply it out. It'll make life easier for you. When I distribute the top, the 9's cancel. This becomes a positive x. X's cancel. So I'm left with the limit as x goes to 0 of 1 over 3 plus radical 9 minus x. When I plug in 0, 1 over 3 plus 3, 1/6. Remember, I'm a notation Nazi too, so make sure you're looking at limit as x goes to 0. Have to keep writing that until when? Until you plug in 0. And again, the reason for that is you want a true mathematical statement. This limit expression is equal to this limit expression. If you didn't have this written here, the limit is definitely not equal to something with x's in it. You know the answer is supposed to be 1/6. So if you say that's equal to that, you're deaf wrong. So keep that limit there. Okay, number 2 was a question from yesterday. Find the value of a to make f of x continuous. We've got x squared plus 4 for sure. So that's this parabola part for any x values less than or equal to 3. So that is built in there. And then we've got this line. And this line, remember yesterday, could be technically anywhere here. So I want to figure out what value is going to make the line connect where it needs to connect. Depending on what value that a is, it's going to affect where this line falls. I want it to be there. Okay, so the only problem is at 3. So we need the limit as I approach 3 from the left of this function to equal the limit as I approach 3 from the right. And as I approach 3 from the left, I'm using the top equation. So that's why I plugged 3 into that, 3 squared plus 4. 3 from the right is going to be using this bottom equation, so plug 3 into that, a times 3 minus 2. That gives us an equation to solve. 13 equals 3a minus 2. A is 5. And if a is 5, these are going to match up exactly like we want them to. And the last one is a question we ended with yesterday. Redefine f of x to remove all removable discontinuities. So here's my original equation. F of x equals x squared minus 9 over x to the 4th minus 81. So remember, in order to find removable discontinuities, first you've got to factor. X plus 3 times x minus 3 for the top. This is x squared plus 9, x squared minus 9 on the bottom. Not quite done. This is difference of squares again. X plus 3, x minus 3. This time we have 2 wholes because we have the x plus 3 factors canceling, which give us a whole at negative 3. And we have the x minus 3's canceling, which give us a whole at positive 3. When they cancel, this is what we're left with right down here. So if I plug either positive or negative 3 into that, since it's squared, I'm going to get 1 over 18 out in both cases. So f of x is equal to the regular old original function if x is not equal to plus or minus 3. So that's where the holes are. Both of those holes get plugged up by the y value of 1/18. So it's 1/18 if x is either positive or negative 3. Now note, this does make the function continuous now, even though there's still a factor on the bottom. Why would that make the function continuous even though I still have something in the denominator? Well, because think about this denominator. What's going to make this 0? Only imaginary numbers. And in calculus, we're not really concerned with imaginary numbers. So there's no real value that's going to make this 0, because this is going to be some number squared, which is going to be at least 0. When I add 9 to it, it's not going to be 0 anymore. Okay, So there's some quick warm-up questions. So that's some limit stuff, and you should expect some questions like that in the quiz in a few days. On to the new stuff. The max-min theorem and the intermediate value theorem. And to illustrate these, I want to look at that other sheet. I think it's kind of at the end of your packet. The max-min theorem and the intermediate value theorem. So look at this first one. This is the max-min theorem. If f is continuous at every point on the closed interval from a to b, then f takes on a minimum value m and a maximum value capital M on that interval a to b. That is, there are numbers alpha and beta within a and b, such that f of alpha equals little m, f of beta equals big M, and little m is less than or equal to f of x, is less than or equal to big M at all points x in AB. Okay, so that probably sounds real confusing to you. And that's because that's how math theorems sound. Really, it's not saying all that much. So let's break this down. If f is continuous, continuous is a key part, it's got to be continuous, at every point on the closed interval from a to b. So here's a, here's b. F is some function, this is just an example, could be any function that's continuous on that interval. Okay, cool. Now this interval is talking about x values, as you can see as they're on the x-axis down here. If it's continuous, so if I can draw this without lifting my pen or pencil, there has to be some maximum value in there, and there has to be some minimum value. You can see them pretty easily. Here's the maximum value, here's the minimum value. And that's within that closed interval AB that I was talking about. Okay, so the maximum value they're calling big M, the minimum value they're calling little m, and this line here, there are some numbers alpha and beta in AB, so that just means somewhere between A and B, there's a value, we'll call it alpha, such that the function evaluated at alpha is equal to that minimum value. And there's a beta, such that the function evaluated at that value is equal to the maximum. Okay, so that takes us to here. And then this last piece here isn't saying all that much. That just says this minimum value and this maximum value, every other function value has to be between those on that interval. Okay? Now remember, continuous is a key part here, because let's see what could happen if it wasn't continuous on AB. Well, if it wasn't continuous, I could throw an asymptote in the middle here, and we could have something like this. Does it have a maximum and minimum value now? No, because this goes up forever and this goes down forever. So there would be no max and there would be no min, because it goes up to infinity and down to infinity. But then this theorem wouldn't even hold, because in order for this theorem to be true, it's if f is continuous. So it's been proven that no matter what type of crazy function you draw, that's not a function, you get the idea. What type of crazy function you draw, as long as it's continuous, there's gonna be a max value and there's gonna be a min value. Okay, well, what about something like this? Here's A, here's B. That's continuous. Is there a maximum value? Is there a minimum value? Well, there actually is. They're just both the same. So that's a maximum value. That's a minimum value. And you could say the same about every other point in here. But look at how it's written. It still holds true. Let's say this is 4. Is 4 less than or equal to f of x, which is less than or equal to 4 for all values between a and b? Yeah, because it's always 4, so it's always equal. So technically, it still holds true, even if it's a straight line. So here's a couple other examples. You can see continuous at the endpoints. Here's one where it's max is at one of the endpoints, but the min is somewhere in the middle. Now technically, this is continuous, but it's not differentiable. We're going to see some other theorems in a couple weeks that have to be continuous and differentiable. We haven't even talked about what this means yet. That's not required for max-min theorem. We'll talk more about it later. Oh, and this is just more of me talking about how a straight line, like what I told you up here already. Okay, so sounds confusing, not all that confusing. All you got to remember is if it's continuous, somewhere between the endpoints, maybe at the endpoints, there's a max and there's a min. Okay, let's talk about the intermediate value theorem. You just read it first and then we'll break it down again. If f is continuous at every point on a closed interval of a and b, sounds like the same as the max-min theorem so far, and n, capital N, is any number between f of a and f of b, then there is at least one point c between a and b where f takes on the value of n. Again, maybe this sounds a little confusing, so let's break it down. If f is continuous at every point on a closed interval from a to b, so I got to have an a, I got to have a b, so a definite start, a definite end, and I'm continuous in between there. So there's just an example. So far this holds true. N, a note, sometimes the book and myself in the notes will use k instead of n. N is any number between f of a and f of b. Okay, so let's keep things in perspective. A and b are x values, right? N is a y value because it's between the function evaluated at a and the function evaluated at b. So here is the function evaluated at a, the one endpoint. Here's the function evaluated at b, the other endpoint. As long as I'm between these values, I can pick any number in between. We're calling it n here, but sometimes it's k. And the intermediate value theorem says there has to be some spot on that function in between a and b where that value is reached. Now, if you think about it, that should make sense again. Think about it. Whatever value I pick between, whatever function I pick between a and b, if it's continuous. So if I have a point at a, have a point at b, and somehow have to connect the dot without lifting my pen, then it should be true that if I pick any value between those endpoints, like there's got to be a place where the function hits, because just by the nature of the game connect the dots, you're going to have to pass through that at some point, right? Right. But it has to be continuous. So here's an example over here. Here's a to b, not continuous. So I've got this little piece over here and this piece up here. If it's not continuous, well then sure, maybe there is a spot where there's a gap where I can't find anything. But if it was continuous, I would have had to cross over that gap. The other thing is that n value, which again sometimes I'm going to call k, must be between a and b. So all I know for sure is I've got a definite start and I got a definite end, and it's continuous. I don't know how these points are connected, so there could be a little dip like this one, but it could just be a straight line too. So anything between those two values would have to get hit somewhere, but if I pick a value outside of that interval, then there's nothing to guarantee that it's going to hit down there. So got to be continuous, and the number we pick has to be between the two endpoints. Keep that in mind. Okay, so that's the two theorems we're dealing with. So let's go back to the notes. Does the intermediate value theorem hold? I'm just going to call it IVT usually, for this value of k. If so, find a c such that f of c equals k. So if f of x equals x squared minus 4, and my interval is between 2 and 5, and k equals 5, does the intermediate value theorem hold? Well, you got to check two things. Is f of x continuous on this interval? So in that theorem I talked about a second ago, this is a and b. So between 2 and 5, is x squared minus 4 continuous? Of course it is. Why wouldn't it be? It's a parabola. It's always continuous. So check. is this value between the start point and the end point? Well, if I plug the start point in, f of 2, 2 squared is 4, minus 4 is 0. Plug in 5, 5 squared is 25, minus 4 is 21. So yeah, I'd say 5 is somewhere between 0 and 21. So yes, k, or n on the other page, is between the start point and the end point. So it should hold that, yeah, there should be some point in here where the function equals 5. So these two things together means the intermediate value theorem holds, and that guarantees I should be able to find some function value, some x value, that equals 25, or sorry, that equals 5, and that x value needs to be between 2 and 5. So c squared minus 4 equals 5. I'm just solving this f of c equals k thing. So literally, f of c would be if I plug c into the equation, c squared minus 4. I want that to equal 5. C squared equals 9. When you take a square root, remember it's plus or minus, but why is it always plus in this case? Well, c has to be in the given interval. So you know about parabolas. You know that x squared minus 4 looks like this. I'm looking where 5 is. Well, obviously, when x is negative 3 and when x is 3, it's going to equal 5. But I wanted it between that a and b. That's what the intermediate value theorem said. Don't believe me? Let's look again. There's at least point c between a and b that takes on that value that we're looking for. So here's 2, here's 5. The value that's between them is positive 3. Okay, here's my second example. F of x equals 2x squared plus 6x on 1 to 5. I want to find k equals 6. Is it continuous? Obviously, it's a parabola. Check. Is the value I'm looking for between the endpoints? Well, if I plug in 1, 2 times 1 squared plus 6 times 1 is 8. Plug in 5, 2 times 5 squared plus 6 times 5 is 80. Nope, that's a problem. 6 is not between 8 and 80. So the intermediate value theorem fails, and we're done. So look at my picture down here. 2x squared plus 6x is this parabola, something like that. But I'm only looking between 1 and 5. So we found 1, the y value was 8. 5, the y value was 80. So sure, the parabola does equal 6 a couple times, but not on this interval from 1 to 5. So the intermediate value theorem fails. There's no value between here where the function is going to equal 6. Make sense? I hope so. Okay, here's the last page of notes. Another example. F of x equals x over x minus 3 on 0 to 6. Is this continuous? Well, be careful. It's a rational function, so no, rational functions aren't continuous. But is it continuous on this interval? The answer is still no, because the discontinuity happens at x equals 3, which is within this interval, so the intermediate value theorem fails. But as a side note, if I had said, is it continuous on 4, 6? Well, sure, it is, because even though this is a discontinuous function, on this interval, it would be continuous, because the only discontinuity is at 3. Okay, but that's not what I actually asked, so don't let me confuse you. Okay, last one. F of x equals 2 plus x minus x squared. This is my AB interval, 0 to 3, and I want to find a function value of 1 if the intermediate value theorem holds. Is it continuous? It's a parabola, so sure, it is continuous. Is my function value between the endpoints? If you plug in 0, you get 2. If you plug in 3, 2 plus 3 is 5, 5 minus 9 is negative 4. So yeah, it's a decreasing function, but it is, this k equals 1 is still between 2 and negative 4. Doesn't really matter that it's backwards. So yes, it is between. So the intermediate value theorem holds, which means I should be able to find a value c such that f of c equals this k value of 1 that I want. So f of c is 2 plus c minus c squared equals 1. So we gotta rearrange. I added the c squared over, subtracted the c, subtracted the 2, set it equal to 0. We could use quadratic formula. Complete the square is a little more efficient, it's a little faster. Let's see if you remember it. I moved the constant over, that's where this 1 came from. We add, remember this is b over 2 squared. I added that to both sides. B, the number in front of this term, is negative 1. So negative 1/2 squared got added to both sides. Remember how complete the square works? This will turn this into c minus 1/2 squared. This is really 1 plus a fourth, so that's where the 5/4 came from. I still want to solve for c, so I take the square root of both sides. Now I get c minus 1/2 equals plus or minus, don't forget that. This is radical 5 over radical 4, which is just 2. Adding the 1/2, we get 1/2 plus or minus radical 5 over 2, but I have to be in this interval. I have to be between 0 and 3. Or maybe you don't know which one is in that interval. So actually type it into the calculator. I did 1/2 plus radical 5 over 2 in the calculator. I saw that it was 1.618, so that is in that interval. So there's a value of c that works. If I did 1/2 minus radical 5 over 2, I got negative 0.618. That's not in that interval, so that's why we can't use the negative answer. Okay, so that was some pretty high-level math, but hopefully that made some sense. If it didn't, come in, sit down with me so we can go over it again. But you should be able to do problem set number 16 now. So try those questions, and if you're getting the right answers, you're on the right track, and if not, come in for extra help.